Now on BBC One, It's About Time, presented by Dudley Moore.
Right, start the clock, please. 30 seconds, studio. Keep it quiet, please. Settle down.
It's about time. End sequence. Take one.
15 seconds, studio. 10, 9, 8, 7, 6, 5, 4, 3, 2.
And the next contestant is Mr. Dudley Moore. Mr. Moore, your general knowledge questions start now. How long is a piece of string?
Pass.
Which came first, the chicken or the egg?
Pass.
How many days make forever?
Pass.
What was happening before the beginning of time?
Oh, this isn't fair. These questions don't make any sense.
Correct.
Correct?
That's right, correct.
Who are you?
Augustine, Bishop Augustine of the Numidian city of Hippo.
Look, hang on. Wait a minute. Look, first of all, I get a load of questions that don't make any sense.
Correct.
Then when I say they don't make any sense, that seems to be the right answer.
Correct.
And then you turn up from a place I've never even heard of, and almost all you can say is correct.
Correct. Oh, I am sorry.
Where did you say you came from?
Hippo, Numidia. The past. I was made Bishop of Hippo in the Roman province of Numidia in the year of our Lord 396, a long time before your time.
Wait a minute. Not Augustine. Saint Augustine?
Well, yes, I will admit that a few centuries after I was dead, they did in fact make me a saint. And I have enjoyed it. Down all the centuries, I have found it most enjoyable, most enjoyable.
What brought you here?
Time.
Time.
Time. It was that last question that was put to you that drew me here, because I put the same question to myself, although in a slightly different manner.
How?
Well, I asked myself, what was God doing before he created heaven and earth?
And what answer did you give yourself?
Well, I came to the same conclusion as you did, that the question cannot properly be asked. Although it did occur to me that if God was doing anything, he was perhaps devising punishments for people who pry into mysteries. Oh, yes, there are a lot of questions which cannot be asked. Some are too vague, like the how long is a piece of string one. I mean, you must specify what particular piece of string.
Right.
Others, like the what was happening before the beginning of time one, contain their own implicit contradictions. I mean, the word before implies the passage of time. So the questioner is cheating. He is using the concept to frame a question about the one event in the universe to which it is inappropriate, namely the beginning of time. So you're quite right. The question is quite senseless. And that is the trouble with a lot of questions about time. Very few of them are answerable. That is why philosophers down all the centuries have always puzzled about the meaning of time.
Well, everyone knows what time is.
Oh, but do they? What about concepts like becoming, change, constancy, permanency, the past and the future, now and then, before and after? What about that, for example?
What? The candle?
The candle flame. It is obviously the same candle flame from one instant to the next, and yet it is constantly changing. Does that make it a different candle flame? I don't think you will find the concept of time as straightforward as you imagine.
You're beginning to confuse me now.
Good. In that case, you are beginning to understand.
What is time?
Time? Why don't you begin at the beginning?
Thank you, thank you. And now, for a little piece entitled Back to the Beginning of Time. Thank you.
Oh, ready when you are. Sorry.
Did our universe have a beginning? Could you leaf back through the pages of the cosmic history book and arrive at page 1? We may never know. Today's theoretical physics can really only hint at what we might find on the first page, indeed, the first few pages of the story of time. What follows is a description of how it may have been. A description cosmologists have drawn up by pushing theory into the realms of imagination. That having been said, however, the first imaginable moment after the beginning of time may prove to be after only one 10 million millionth of the first second had passed. This unbelievable number, a 1 with 43 zeros in front of it, would then represent the shortest length of time that can exist in the universe. The temperature would have been a distinctly tropical 100 million degrees, and little is known of what might happen at such temperatures. It would have been an intensely, inconceivably violent moment. The very fabric of space itself may have been juddering, creating waves of gravity that will have set the universe ringing like a bell. Some cosmologists believe that during this period of twisting and buckling, exotic particles of matter would have been created straight out of empty space, damping down the turbulence in our expanding universe. But as the first millionth of the first second of the universe had passed, when its size could already have been as much as 10 kilometers across, countless numbers of those extraordinary particles that we saw before would have disintegrated and decayed, many of them never to appear in the universe again. Quite a bit further on, everything had cooled, if cooled is the right word, to 100,000 million degrees, 7,000 times hotter than the center of our sun. There are no atoms or molecules yet, though. It's still far too hot for them to exist. For the moment, it's a raging furnace in which matter, antimatter, and radiation are crammed together into a universe that may already be 40 million kilometers across. As the universe became 1 second old, the temperature was still easily high enough for bizarre but crucial events to be taking place. Until now, the universe had contained roughly equal amounts of matter and antimatter. What imbalance there was a tiny one. But by the time it was celebrating its first second of existence, most of the particles of matter in the universe had been destroyed by colliding with particles of antimatter. The result of these collisions? Light. Saturated with light, and now containing only a relatively small amount of matter, 13 more seconds were needed before the universe was cool enough for the nuclei, the central portions of atoms, to be formed. It was now a mere 3,000 million degrees in the shade, so to speak, and the universe should have been ready to start building the atoms of the first compound element on its list, an element called helium. It should have been ready, but it wasn't. The weak link was a terribly fragile type of hydrogen known as deuterium. Although everything else was all set to go after 13 seconds, it was still too hot for deuterium to be stable. The universe had to drum its fingers and wait. Wait for another 3.5 minutes. At the age of 3 minutes and 46 seconds, it was ready to take its next big step. It was now cool enough for deuterium to be stable, and at last, nuclei of helium could be made. It was the penultimate step in the formation of normal matter. So far, it's taken slightly longer to describe what was happening than it actually took to happen. Our universe, at last able to create the odd helium nucleus, is just 4 minutes old. The final step took rather a lot longer. In fact, the universe had to wait fully 700,000 years until the temperature dropped sufficiently for the atomic nuclei to be paired up with their electrons. Then, for the first time, the universe was well and truly divided into recognizable atoms of matter and energy. As eddies in the universal gas clumped together under gravitational attraction, galaxies and stars could at last be formed. Today, the universe is about 15,000 million years old. Many millions of stars have long since had their day and have died away. And certainly in human terms, that makes the universe seem unimaginably old. But for our still expanding universe, the day is yet young, and time has only just begun. How long was that?
What?
How long was the film?
Well, it seemed to go quite quickly, but there was a lot in it. I'd say about under 10 minutes, but not a lot under.
In fact, the sequence that Dudley was watching lasted for 6 minutes and 21 seconds. The difficulty he faced was a common one, namely trying to judge two different sorts of time. Time past and time passing.
May I speak to you for a minute?
Go. You have 58 seconds.
Well, in glancing at your books, I noticed that in the columns marked...
You have 48 seconds left. Hurry, hurry.
Oh, I glanced at your books, I noticed in the...
28 seconds. You're running out of time.
Mr. Bialystok, I cannot function under these conditions.
Who could? But wait a moment. Was that really a minute? Or did Mr. Bialystok cheat?
May I speak to you for a minute?
Go. You have 58 seconds.
Well, in glancing at your books, I noticed that in the columns marked...
You have 48 seconds left. Hurry, hurry.
Oh, I glanced at your books, I noticed in the...
28 seconds. You're running out of time.
By the time the accountant had given up his race against time, believing the minute to be over, only 15 seconds of real time had passed. No wonder it all proved too much for him. You see, estimating time as it passes relates to the way in which we direct our attention, and it can vary enormously depending on whether we're busy or bored. On the other hand, an estimate of time that has passed depends on how we classify or pigeonhole what we were experiencing. For example, this is a list of the sequences included in this program so far. It tells us what we've seen in the order that we've seen them. We know that the film describing the early universe was 6 minutes and 21 seconds long. But how long were the other sequences? And how much do they add up to? Was that more or less than you'd expected? It's been a pretty ordinary day for the Tempo family. Mrs. Tempo has had the traditional hard day at work, being nice to the boss, being less nice to the people under her. Her son has had an equally traditional day studying at school. He was studiously bored and spent a lot of time gazing into space and doodling jet aircraft in his notebook. And it seems to Mr. Tempo, who's been at home all day doing the housework, that most of his time was spent waiting for the water to boil. For each member of the family, the way they perceived time during the day was different.
I'm home, Teddy. All right, darling. Have a busy day.
Awful.
Non-stop all day.
For the busy Mrs. Tempo, the day has sped by, filled with a wide range of attention-demanding activities, and yet, despite the fact that her time passed quickly, when she came to look back on the day, having to pigeonhole such a wide variety of activities makes it seem long.
I can't believe it's only Wednesday. It felt like a year since the weekend. Oh, darling. Cheers, Fancy. Oh, hello, Patrick. What sort of day did you have then? That's all right. Same old stuff.
He'd had a boring day. He daydreamed a lot, doodled quite a bit, and listened hardly at all. Time, at the time, had seemed to pass very slowly, and yet, because his school routine can easily be pigeonholed, when he looks back on his day, it seems short, and the weekend not far away.
So it'll soon be the weekend. Any tea? I'm afraid not. A watched kettle never boils.
Of course, the old adage about a watched kettle never boiling is untrue. It's an illusion that results when we wait for time to pass. What happens is that while we are waiting, our attention focuses on smaller and smaller intervals of time. The illusion of lengthening time that this produces can often happen when watching the second hand of a clock. The closer one looks, the slower the hand seems to move. Because waiting for time to pass, timing time, in other words, appears to slow it down. So it looks as if these variations in our awareness of time depend on how we're thinking. Thinking about passing time, past time, or time. But what happens to time when we're not thinking? When consciousness has been taken away?
Are you all right? What are you doing after the op?
Now then, Mr. Moore, all you'll feel is a tiny pinprick.
Now just start counting to 10.
1, 2, 3.
Deeper than the deepest sleep, anesthesia literally chops hours out of our lives. As far as we're concerned, one moment it's 10 to 10 in the morning, and the next it's 10 past 3 in the afternoon. Half a day in which time ceased to exist, simply because we were unconscious. What it boils down to is that time is thinking, is consciousness. What's that you're playing?
It's a jazz piano style I learnt from Merrill Garner.
Ah.
It seems to me rather like time.
Really? How?
Well, the right hand is moving in our human perception of time, sometimes fast, sometimes slow, while the left hand is chugging along in a sort of absolute time, you know, hours, minutes and seconds type time.
Except that it isn't like that.
Huh?
Well, not really. You see, it's the idea of absolute time that's misleading.
Well, what is this measuring? If not identical intervals of time? After all, a second is a second is a second.
Unfortunately, it's not that easy. For centuries, a second was defined in terms of the Earth's rotation. But now it's known that the Earth doesn't keep good time.
Why?
Because its rate of spin varies. Oh, it's not a big effect. It only amounts to a few microseconds a year. But when you look back to prehistoric times, the result of this variation was a day that was only 21 hours long.
Okay, so the Earth isn't very punctual, but what about atomic clocks? I mean, they measure absolute time, don't they?
Well, it's certainly true that they're accurate, incredibly accurate, losing or gaining only 1 second in as much as 300,000 years.
That's useful.
Very. But even these clocks don't measure absolute time.
Why not?
Well, because there's no such thing. Or, to put it more accurately, the concept doesn't mean anything. This is Isaac Newton. He believed in the existence of absolute time. He imagined it to be, as he put it, flowing steadily without relation to anything else. He believed in absolute space, too. On both counts, he was wrong.
He was? Why?
Well, because although most of his theories were drawn from observations of the everyday world, his notions of space and time were drawn from no more than religious conviction and what he held to be common sense.
That's bad.
I'm afraid so. He wouldn't see that the notion of absolute time is misleading.
Why?
Well,
Go on.
Well, it's all very... Did you ever meet Albert Einstein?
Albert Einstein? No.
Meet Albert Einstein.
Hello, I'm Dudley Moore.
Albert Einstein.
It's about time.
Excuse me?
I'm trying to find out about time.
Ah.
You see, but what I thought I knew to be true turns out to be false, and now I don't really know where I am.
Shall we?
Yes, of course.
Let us, for the moment, lay aside our assumptions about knowledge and common sense.
Right.
In this instance, imagination is more important than knowledge.
Right.
Let us imagine how our universe would be if we were to reject Newton's ideas of God's absolute time and absolute space. Instead, consider what happens if we assume that the speed of light is constant whenever you measure it.
Light? What's so special about light?
Special? It is the most special of anything. You can't speed light up or slow it down or change it. Whenever you measure it, its speed is always the same.
I don't quite see.
But you see, if this were not the case, then all sorts of things could happen. A beam of light could catch another beam of light. Well, then could you imagine how mixed up our world would be?
Yeah. But what does this have to do with time?
Well, you see, a mix-up like this cannot happen. God is sophisticated, but not malicious. Now, if the speed of light is constant, then in order to make sense of everything, other aspects of our universe must be allowed to vary.
Such as time?
Space and time. But let's stick to time for the moment. In 1905, when I published my paper outlining these principles of the constancy of the speed of light and relativity, it was found that one could prove that a clock that's traveling towards or away from an observer runs slower than a clock that he believes to be stationary. Mind you, the amount of slowing that occurs only becomes really noticeable when the speed of the moving clock is near to the speed of light.
But how do you check your theory? I mean, surely nothing travels fast enough to produce this effect.
It's happening all the time.
Well, how... Albert?
10 kilometers or so above us, nature's own moving clocks are being created by the collisions between high-energy particles coming in from deep space and atoms in the atmosphere. These clocks are, in fact, very short-lived, high-speed particles called mesons. Muons for short. After only 2 microseconds spent traveling at almost the speed of light, they break up into other particles. There would seem to be little point, therefore, in setting out a muon counter at sea level in the hope of catching a few. And yet, that's precisely what 2 physicists in America did. After measuring the number of muons entering their equipment at the summit of Mount Washington, 2,000 meters up, they dismantled their whole laboratory and took it down to sea level. What they found was that many of the muons survived this extra distance because time, when seen from the point of view of the high-speed muon, passes 9 times more slowly than it does for you or me on Earth. 2 microseconds of muon time is 18 microseconds in Earth time, and that's easily long enough for them to reach the sea level laboratory before expiring.
You ready for this paradoxical experiment, then? Oh, that would be the twins paradox experiment, Dad? Quite right, Dad, yes. Yeah. Well, the trouble is, I don't know why have they chosen us for it? Because we're twins, you twit. You know what happens, don't you? No. Fine. One of us goes zipping off into space at practically the speed of light, while the other one remains here on Earth. Now, when I get back, I beg yours, when whoever gets back, they discover some amazing effects. Oh, it's nice. Oh, it's lovely.
Many concepts in physics are first posed as thought problems. And one of the most famous is called the twins paradox. It refers to the curious discrepancy in the amount of time that would pass for each twin if one of them were to go off on a space trip. Let's imagine that throughout the trip, the astronaut twin spacecraft is accelerating at 1 Earth gravity, 1g, just for comfort. After a voyage of 12 years, during which time his speed would have climbed to 99% of the speed of light, he would return to find that his twin was now an old man, for whom 50 Earth years had passed. And bizarre though that may seem, if he'd chosen to spend his entire life zipping off to Andromeda and back, a journey that would take 56 years, accelerating at 1g, on his return he would find that 4 million Earth years had passed. Now, these effects are not only real, they have already been experimentally observed. A few years ago, atomic clocks were loaded onto commercial jets and flown around the world. It was found on their return that previously synchronized clocks now told different times.
Well, how big was the effect?
Well, when traveling westwards, the clocks gained 160 nanoseconds, and when traveling eastwards, they lost 50 nanoseconds.
Nanoseconds? Is that a lot? What's a nanosecond?
Well, that's not much, I'm afraid. A nanosecond is only 1,000 millionth part of a second.
Not very much.
No, you're right.
Still, it's a sort of time travel, isn't it?
In a way, yes.
I've always fancied time traveling myself.
Really?
Yeah.
Oh, that can be arranged.
Come, Mr. Moore. We can't have you lying round here, or we'll never get you to New York for 10 o'clock.
It's 11 o'clock already.
Now, we're not trying to be difficult, are we, sir?
Good book?
Oh, brilliant.
Oh, Dudley Moore.
Isaac Asimov.
The very man. I'm still rather confused. Here we are, travelling on Concorde. Now, are we travelling forwards in time or backwards in time?
Both, actually. In the first place, there's a relativistic effect, which sends us forward in time, just a very small amount, a few nanoseconds, because we're traveling faster than we would be if we were in a ship, and certainly faster than if we were standing still. We're only going at about a millionth the speed of light, but that's enough.
Menus, gentlemen.
Oh, lunch.
No, it's breakfast, actually.
That's the other side of the coin. The relativistic effect is virtually nothing. It's insignificant. But the subjective change is quite large. We left at 11:15. We'll arrive better than an hour before that by the clock, because this plane is taking 3.5 hours to cover the distance that the Earth would have to cover in 5 hours of turning.
Right.
So you see.
But what about really travelling backwards in time? I mean, as they do in the books.
Fiction, dear boy, fiction. There we run into trouble with cause and effect. Let me show you. Cause, loosening of the grip. Effect, the false. Or, to put it another way, before, after. Now let's see where that leads us if we take a more complicated example. Imagine that I've gone back in time to Russia in 1918 to find my father, and because I'm a callous sort of youth, I decide to shoot him. Well then, he crumples up and dies. But then, once he's dead, I can't possibly have been born, so I couldn't have built a time machine to go back to Russia in 1918 and find my father, which means he's alive. But if he's not dead, then I was indeed born. I could build my time machine, go back to Russia in 1918 and come... Well, you see what happens.
Yeah. So, traveling backwards in time is really impossible. But what about traveling in the future? I wouldn't think the same things would apply, would they?
No, we know from time dilatation and the twin paradox that travel into the future is possible. But then supposing you want to come back again. You've gone 1 week into the future and you don't fancy what you saw. And you feel that if you come back, you'll change things, and it won't happen. That would mean that what you saw was one of an infinite number of futures, which you can cause not to happen.
Right.
On the other hand, supposing it turns out that you come back, but no matter what you do, the future is as you've seen it, in which case things are determined. We live in a determinate universe, and it's not a matter of choice for us to decide whether we're going to go into the future or not.
I wonder which it is. I mean, I feel like I'm free to do things. Go to the theatre or not, have a cup of tea or not. Anyway, I've just proved it.
Really? What have you proved?
Well, I didn't have to stop the film here, did I?
Didn't you?
No.
All right. Have a look at the next frame of film.
Oh, there isn't any more.
That's right.
Oh, that's mad. I stopped the film purely haphazardly, and just by chance it happens to be the last frame in the sequence.
Maybe it wasn't chance.
That's weird.
Go on a bit. Let's see if we can come to a few conclusions about whether or not the future is determined.
What's coming up next?
Well, of course, the first thing we have to do is draw a Minkowski diagram.
A Minkowski diagram, yes, of course. How silly of me.
First, let's draw a grid of the 3 dimensions of space. Up and down, left and right, and forward and back. Okay, stop there. Now, our 3 dimensions are caught at a point in time, namely our single frame of film.
Okay.
Now, if you would, move the film on a couple of frames, and to simplify things, we'll take away the dimensions of depth and up and down. Okay, hold it there for a moment.
Right.
What we're left with is a single dimension of space frozen on our stationary frame of film. Now, let's draw onto this single frame of film a direction of time from bottom to top, and a point which lives its life entirely confined to this one dimension. It only ever moves to the left or right, in other words. Now, if you start the machine, joining up the frames of film, the instants of time, then you can see what our twinkling point is up to. Mathematicians call the track it's leaving, as it weaves back and forth, a world line, tracing out our point's life history, so to speak. Its birth, where it went in space, and when it died. This way of looking at events is extremely useful to mathematicians, who usually draw the diagram something like this. The vertical line is still the direction of time. The horizontal line, still space. These radiating lines represent the tracks of the fastest things in the universe, namely light beams, and so they're called light lines. Their crossing point is the present, the now.
It looks like an hourglass.
Yes, there are some strong similarities. Ahead of the now is a region called the absolute future, like the sand in the hourglass that's yet to fall. Behind the now is a region called the absolute past, equivalent to the sand that's already fallen. To either side, there is a region of space and time about which, for the moment, nothing at all can be known, called the absolute elsewhere.
The absolute elsewhere?
Yes. Totally inaccessible to anyone experiencing a now, since not even light can reach them from out there until sometime in their future, further along their world line, in other words.
What about free will, though?
Now, you'll see. All in good time. Go on a bit more. Let's make this your world line from birth to some time in your future. According to Einstein and others, time simply is. It doesn't flow. You're the one that experiences the motion through time.
It's moving.
Well, that's right. It's your now. Your consciousness of the present moving along your world line, discovering new aspects of your life as you come upon them. Some people believe that the bit of your world line that extends into the future is already there, and that things don't happen to you, you happen to them, simply stumbling into them in the dark, so to speak.
But that seems to imply that I'm not free to choose my own fate.
That's right, it does. Of course, many people disagree with this view of our lives. Some people think that there's an almost infinite variety of futures available to us at each now, and that we're free to choose any one of them. But in fact, since there's no way of proving which view is the right one, and so long as we believe ourselves to be free, what difference does it make? And the only thing we can't change is how quickly we reach the end of our world lines.
I don't like the sound of that. Can't I stop it?
No.
Slow it down a bit?
Sorry.
Stupid machine.
Now. 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 What does that word now really mean? You might say that it describes the gap between the future and the past. And yet those Minkowski diagrams imply that the now is infinitely short. If it is, then time must be continuous. But what if time were discontinuous? What if there were particles of time, like the grains of sand in this hourglass, each of which couldn't be split up any further? If that were the case, then each particle would represent the smallest moment possible. Now, in other words. Some theoretical physicists think that's the way time is. Dr. David Finklestein.
The main thing to remember is that while time may be very hard to talk about, it's not itself a hard thing, like a piece of flint, like this. Time is the relation between things that happen. If you like, time is just one damn thing after another. As soon as we learned that electricity came in bits and energy came in bits, we began wondering whether time did too, and space. And these bits were called chronons. These bits too aren't material objects. They've got to be events, happenings, the things of which time is made, like the sun going down. The question of whether they exist is a question of whether the things that go on in the world are a steady stream that can be cut anywhere we like, or whether, in a sense, God too has an hourglass with grains of sand in it that fall one by one. I don't think most people realize how far physics is from a theory of the world. I think people trust physicists too much. There has never been a theory of the world. Newton didn't have one. He had at best a doctrine. Find the forces was his doctrine, and you'll understand everything. Today we have a doctrine of elementary particles. The characteristic time for elementary particles is around 10 to the minus 23 seconds. This is roughly the time it takes light to cross a particle at rest. If the chronon were that big, then it would be important for the structure of elementary particles, matter, and the rest of the universe. I'm hoping that that's about where the answer is, and that the bewildering variety of particles we've been discovering recently is just a reflection of the different ways in which elementary processes weave together. The other possibility, an extreme one, is to ask how small a division of time can be made before the energy required to make that division gets so large that it in turn creates a black hole that swallows up the event. That time is around 10 to the minus 42 seconds. The very question of the continuity of nature has been with us as long as people have worried about time at all. Heraclitus said that time is as a child playing checkers. Zeno 5 centuries before Christ, raised the following paradox. Let's get my old friend the flint back again. Zeno considered the following experiment. If we drop it, it hits the ground. Then he proved that couldn't happen. Because in order to reach the ground, first it has to fall halfway. Then it has to fall half the remaining distance. Then half the remaining distance. Then half the remaining distance. If you can always cut the distance that remains in half, it seemed to him it took an infinite number of acts before it could reach the ground. How can you carry out an infinite number of acts in a finite time? Therefore, it never reaches the ground. It's an infinite sequence that never terminates. We are all immobile, according to this argument of Zeno. Before we can move any distance, we must move half that distance, and so on. Lord Russell, back about the beginning of the century, used the movies to convince himself that just because life looks continuous is no reason to suppose that it actually is, because the movies, too, are one frame after another, and yet give this illusion of continuity. The main question is, if there are chronons, if there are frames in the world motion picture, how many frames per second is the show going on at?
This continuity in the world motion picture show, the fact that we do see time as just one thing after another, has given rise to a concept known as the arrow of time. It refers to something so basic we're hardly aware of it, and yet as sure as one day follows the next, if it changed, life would be unlivable. What is this strangely powerful concept? Quite simply, it is the fact that one day does always follow the next, that time does always flow in a single direction, from the future to the present and into the past. Time's arrow, in other words, always seems to point the same way. And perhaps it's just as well. After all, a clock whose hands occasionally went forwards and occasionally went backwards might be worth something as a curiosity, but as a means of telling the time? We live in a world of endless one-way changes, and we become aware of time by observing these changes. Changes in the position of the hands on our clocks, changes in nature, and changes in our consciousness of events. It seems obvious to say that our awareness of time is not an every now and then sort of experience, that sometimes runs forwards and sometimes runs backwards. And yet, if the interactions and collisions of atomic particles were our only guide, it would be very difficult to say which way time was going. Imagine that these billiard balls are atomic particles. Now, some of these sequences have been reversed. Can you tell which? When balls pop up out of the pockets, of course, it's obvious. But by and large, each collision looks right. In other words, it behaves according to our expectations, whichever way you run the film, forwards or backwards. But as we've already seen, our large-scale world isn't symmetrical in time. Once we start to look at larger and larger groups of particles, the arrow of time becomes more and more apparent. Although it's possible that all these balls could arrive at the same place, at the same time, with just enough energy to cancel out each other's motion, sending the white cue ball up the table to be stopped by the cue, it is rather unlikely. It's this unlikeliness that gives time its arrow. Let's look at what's happening in this beaker. Here, Instead of a few particles, there are literally billions. The molecules in the crystals of our sugar arrow are jiggling about in a fairly ordered way, while the molecules of water are moving around in a random fashion much more quickly. For the moment, it's a fairly clear-cut and organized arrangement, but one of the universal laws of nature predicts that this cannot last. There is an overwhelming tendency in physical systems for orderliness and organization to break down into disorderliness and chaos. The measure of this increasing chaos is called entropy, and inevitably, as the entropy in the system increases, the outcome of this experiment will be a beaker full of reddish, sugary water. So the universal arrow of time always points towards the future, because each moment is in a greater state of disorder, in a mathematical sense, than the moment before. It is, after all, a more precise way of saying that, given time, everything decays.
So, we observe the universe to be expanding, entropy to be increasing, and time marching endlessly into what we call the future.
Yes. Why?
Well, if everything was reversed in our universe, we wouldn't really notice the difference, would we? I mean, if everything obeyed the rules and everything went in the opposite direction, I mean, if all waterfalls flowed upwards and if all planes flew backwards and if all food went the other way.
Yes, quite, of course, yes, you're absolutely right. So long as everything obeyed the rules, we'd never know the difference. After all, a time-reversed human being would have a time-reversed brain, capable of remembering the future and predicting the past. And despite the fact that to us everything would look distinctly strange, the time-reversed inhabitants of that world would find nothing particularly odd about their lives. There wouldn't even be anything strange about the contents of a beaker, like this, arranging themselves into clear water and a red sugar arrow.
I don't quite see.
Well, remember, the arrow of time is really no more than a measure of probability. What's happening in this beaker is certainly improbable, but not impossible. If you waited long enough, the motion of the molecules in the beaker could reassemble our sugar arrow. But you'd have to wait a very long time.
All right. Well, in our universe, for instance, how long would it take for the chance movement of the molecules in this beaker to reassemble the sugar arrow, which is in here somewhere?
Well, back at the turn of the century, a French mathematician called Henri Poincaré suggested that provided you sealed it off from the outside world, you could calculate what's called the recurrence time of any event. In this case, it would be about 10 to the power of the number of atoms in the beaker, which, let's say, is 10 to the 25.
Oh. That's 10 to the 10 to the 25 seconds.
That's right.
Oh. That's a very long time.
Oh, yes. It could be quite a bit beyond the end of time.
The end of time? Is there something you're not telling me?
Pardon?
Well, you mentioned the end of time. I'm not sure I like the sound of that. I mean, if it's going to come soon, I'd quite like to make a note of it in my diary, you know. End of time, no appointments today.
Don't worry. It's still a long way off.
Oh, well, that's a relief.
In fact, in cosmic terms, we've only just begun.
Good.
Right at the moment, our universe is about 15,000 million years old, and there's some debate about what it's eventually going to do. The outcome hinges on, of all things, an estimate of how many atoms there are in the universe. If there are enough to exceed what is called the critical density, then the gravitational attraction they have for each other will continue to slow the expansion down until about 50,000 million years from now, it will stop, like a ball that's motionless at the top of its curve. Then the universe would begin to fall in on itself, slowly at first, until 50,000 million years later, it would be exactly the size it is now, but contracting. After another 15,000 million years, it would return to those unimaginably hot, dense moments that were occurring at its birth. Both space and time will then come to an end, and our universe will cease to exist. Some cosmologists have suggested, however, that such a cycle may continue, heralding the birth of another universe. This would mean that ours may simply be one of an infinite number of universes bouncing endlessly in and out. Nobody will ever know. Nothing, not even time, could survive those moments in between when the universe occupies no space, but is infinitely heavy, infinitely hot, and infinitely small.
Right, so the end of time may be 100,000 million years in the future. Does anybody know whether there are enough atoms in the universe for gravity to overtake expansion?
No, not really. Although if current experimental evidence turns out to be true, there aren't enough atoms in the universe. There is, on average, only one atom of visible matter for every 100 liters or so of empty space, and that's only 1% or so of that critical density. Black holes and other strange astronomical creatures may alter this figure, but at the moment, it looks as if the universe has a rather empty future. In 5,000 million years, our own sun will have expanded to engulf the inner planets, including the Earth. It will then collapse, becoming an incredibly dense object, about the size of the Earth, called a white dwarf. Indeed, a piece of a white dwarf, the size of a sugar cube, would weigh over 5 tons. After another few million years, it will have cooled to no more than an icy lump moving silently through empty space. One by one, although new ones will be created from time to time out of the galactic dust, the stars in the heavens will begin to go out. Some will blow themselves apart as supernovae. Some will collapse into black holes. And many, like our sun, will simply dim and cool. As the expansion continues, the fading galaxies will gradually disperse and become invisible. And even the few giant black holes that are left may eventually disappear through a process akin to evaporation. There may be occasional flurries of activity as neutron stars or black holes collide, lighting up the darkness in remote corners of the universe. But basically, that will be that. All that will be left of the universe will be black, empty space. With nothing left to happen, no events left to occur, the concept of time will cease to have any meaning. We will have arrived at the end of time.
Good night.
Right, thank you, studio. Hang on a moment, will you? Just waiting for the... Yes, okay, I will do. We're just waiting for the... Yeah, okay, good. Right, thank you, studio. That's the clear. Thank you very much.
Bit of a bleak end to it all, isn't it?
No, I thought you were fine.
No. No, time, the universe.
Oh. Yes? Yeah, well, okay, I'll see you in a minute, okay?
Sure.
Sorry, Dudley, you were saying?
No, it's the end of time. It's a bit difficult to grasp. Makes all this seem a bit, pointless.
Yeah. Well, I must be getting on. Tempus fugit and all that sort of thing. Yeah?
Fugit, Walter.
about time.
How did you get on?
Well, I'm still confused. But at least I know why I'm confused. It's because time is confusing. Seems to be much more than what clocks measure. Seems to be an idea more than a thing, and yet we experience its passing all the time. All the time. As something very real.
Oh, yes, very real.
I think I've got an unaskable question for you.
Prying into mysteries?
Yeah, well, let me ask it anyway.
Yes.
What is time?
Yes.
Well?
I once asked myself that, long ago. But I found that every answer I came up with, I discovered that I could disprove it. Oh, there was one exception. One answer I thought was accurate and honest.
What was that?
If I am not asked what time is, I know. But if I am asked to explain it, I know I don't know.
At the third stroke, it will be 10, 41, and 10 seconds.
On BBC One tomorrow night, sport.